Welcome, dear students. Today the topic which we are going to discuss is group 1 elements, their atomic and physical properties and the reasons. In this slide we will discuss atomic and physical properties of the group 1 elements. Those elements are lithium, sodium, potassium, rubidium and cesium. These are the elements of group 1A and they are also known as alkali metals. Why they are known as alkali metals? Because the oxides of these elements are basic in nature and they yield alkalis when dissolved in water. Hydrogen is not included in the alkali metals. It is placed above the alkali metals, but their position is ambiguous. And further we will study their trend in atomic radius, first ionization energy, electronegativity, melting and boiling points, density. Trends in atomic radius. The atomic radii, it increases from top to bottom in a group, as it is clear from the graph that from moving lithium to cesium, the atomic radii is increasing, the atomic radius is increasing. The reason is from moving from lithium to cesium, from each element, in each element there is an addition of one new extra shell, one new layer of electrons, and due to increase in the number of shells from top to bottom, the atomic radius is increasing. The radius of an atom is governed by the number of layers of electron around the nucleus. The number of layer of electron means the number of shells which an element has. The pull the outer electron field from the nucleus. This is the attractive force which is between the nucleus and the electrons. That means the effective nuclear charge. Let's compare lithium with sodium. The electronic configuration of lithium is 1s2, 2s1. Sodium is 1s2, 2s2, 2p6, 3s1. As it is quite clear that in lithium there are two electronic shells, two layers of electrons, and in the case of sodium there are three electronic shells, three layers of electrons, so the size of sodium will be greater as compared to lithium. If we discuss the strength of the attractive forces of the nucleus and we compare, we can say that the net pull of +1 charge is from both the nuclei, but in this case, as the number of electrons they are greater, as the number of inner electrons are greater, so we can say that the positive charge on the nucleus is cut down by the negativeness of the inner electrons. That is, the effective nuclear charge become less dominant in the case of sodium. So we can say that we can only say that due to increase in the number of shells, the size of sodium is greater as compared to lithium. In the case of lithium, there are 3 protons. In the case of sodium, there are 11 protons. The number of protons are more in the case of sodium, but as the number of shells of electrons are greater, so we can say that this attractive force of 11 proton is cut down. Trends in atomic radius. The only factor which is going to affect the size of atom is the number of shells of electrons or the layers of inner electrons which have to be fitted in around the atom. Obviously, the more layers of electrons you have, the more space they will take up, and as a result, electron-electron repulsions will occur, and as a result, the atom size will expand and get bigger. Now comes the first ionization energy. Definition. First ionization energy is the energy needed to remove the most loosely held electron from each of 1 mole of gaseous atom to make 1 mole of singly charged gaseous ion In other words, for 1 mole of this process. The equation is as under. First ionization energy means that you are removing electron from a neutral atom, most loosely held electron which is present in the outermost shell. Because it is most loosely held, it can be easily taken away. We will consider the gaseous state. Why? Because in gaseous state, the atom is free from all types of attractive forces. Explaining the trend of ionization energy. Ionization energy decreases, as it is obvious from the graph. As you move from lithium to cesium, the ionization energy decreases, it falls. The reason is the charge on the nucleus, the amount of screening by the inner electrons, the distance between the outer electrons and the nucleus. As we know that the ionization energy, it is inversely proportional to atomic size. If the atomic size of an element is greater, the ionization energy will be less. As you know that atomic size increases from top to bottom, so ionization energy will decrease. Among alkali metals, the size of cesium is higher as compared to lithium. So the ionization energy of cesium will be less in this case. The ionization energy of lithium is highest because its atomic radii is less and it has more attractive forces. As the distance between the nucleus and the outer electron increases, it becomes easier to remove the electrons. As we know that we have discussing here first ionization energy. But if we want to remove one more electron from this singly positive ion to form a dipositive ion, in the case of alkali metals, it will not be possible. Because in the case of first ionization energy, the electron has to be removed from a neutral gaseous atom. But in the case of second ionization energy, we have to remove electron from a singly positive charged ion. As you know that it has positive charge, the charge on the nucleus is greater, the attractive forces is stronger, so more energy will be required. And we know about the electronic configuration of the alkali metals, that in this case the outermost one electron present in the outermost shell will be taken off. But in the case of this particular ion, it is a noble gas configuration. So to remove electron from a stable electronic configuration will be tough. So second ionization energy of alkali metals is very high. That's why the possibility of formation of dipositive ion is ruled out. Electronegativity. Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electron towards itself. According to Pauling's scale, the highest electronegativity element in the periodic table is fluorine, which is 4. What is the reason behind the decrease of electronegativity? It is again atomic size. As we have already discussed in previous lectures, that electronegativity, ionization energy, they are all inversely proportional to atomic size. Small size atoms have higher electronegativity as compared to large size atoms because their attractive forces will be stronger. As we know that group 1a is the first most group of the periodic table, and from moving left to right the atomic radius decreases. So we can say that among all of the groups, group 1a element will be having the maximum size from left to right. So maximum size, that's why they will be having less electronegativity. If we consider the trend from moving down the group, so as you know that it is again inversely proportional to atomic size, so the electronegativity falls as we go down the group. The atom become less and less good at attracting bonding pair of electrons because of increase in atomic size. Imagine a bond between sodium and chlorine. This is an ionic bond, and as you know that the bonding pair of electron is attracted more towards the chlorine atom because it is highly electronegative, and sodium is having less electronegativity. It is electropositive in other sense. The electron pair will be dragged towards the chlorine because there is much net pull from the chlorine nucleus as compared to sodium one. So chlorine will got partial negative charge due to higher electronegativity, and sodium will be having partial positive charge due to less electronegativity. So alkali metals are having less electronegativity. Next comes the melting and boiling point. What is meant by melting point? At melting point, solid is converted into liquid state, and boiling point is the temperature at which liquid state is converted into vapor phase. And we know that the strength of intermolecular forces matters a lot in determining the melting and boiling point. As we are considering here metals, alkali metals, so we will compare the strength of metallic bond in all of these elements, all of these metals, to understand the trend of melting and boiling point. Melting boiling point, it decreases as we go down the group. As they are all metals, so they will be having metallic bond. When we move down the group, the atomic size of the metals, they are increasing. The metallic bond is getting weak. So it can be easily boiled when we or melted when it comes to cesium. So we can say that the decrease in the melting and boiling point, it reflects the decrease in the strength of metallic bond. If we compare the strength of metallic bond in lithium and cesium, we can say that the metallic bond strength is far greater in the case of lithium, and it is due to small size of lithium and more closer packing. In metallic bond, the metal atoms, they are held together by the attraction of nuclei to the delocalized electrons. As the atom get bigger, the nuclei get further away from these delocalized electrons, and so the attractive forces, they decreases. This means that the atoms are more easily pulled apart to make a liquid and finally a gas. Now comes the density. As we know that density is equal to mass over volume. So these are light metals, and the first three members of this group are less dense than water. The density of water is 1 gram per centimeter cube. That means the first three will float on water while the other two, they are heavier and they will sink. As density depends upon mass and volume, it is directly proportional to mass and inversely proportional to volume. And we know that in a group, the atomic mass is also increasing and the volume is also increasing due to increase in the size of the atoms. So when mass increases, the density should increase. And if we consider the volume factor, the density should decrease, because as we move down the group, the volume is increasing. So we will say that we will consider only one factor, that is mass, which is more dominating factor. According to mass factor, the answer of the density is that as mass is increasing, the density of the alkali metals, it is also increasing down the group, as it is obvious from the graph. But there is an anomaly over here, that the density of potassium, it should be higher as compared to sodium, but in this case it is less. There is a abrupt behavior or anomalous behavior in the case of potassium. The reason is that if we look at the masses of these elements, it is 3, it is 11, and the atomic mass of potassium is, it is 6, it is 11, 23, it is 39 atomic masses we are considering over here. So we can say that there is a small change in the atomic masses of these two elements when we move from sodium to potassium, 23 and 39. Okay, but if we consider other elements, there is far difference between the atomic masses of these two elements. Okay, so due to the less difference of atomic masses of the sodium and potassium, we can consider the volume factor over here, and size is increasing. So due to abrupt increase in the size of potassium and less difference of atomic mass values of sodium and potassium, the density of potassium is less than that of sodium. We can say that volume factor is dominating in the case of potassium. Trends in density. The density depends upon two factors, the atomic radius and mass. Atomic radius, basically it affects the volume. So we can say that mass and volume are the main factors, and by changing the radius, the volume of the atom, it changes. As we go down the group, the atomic radius increases, and so the volume of atoms increases as well. That means that you cannot pack as many sodium atoms into a given volume as you can in lithium atoms because of the difference in their sizes. However, as we move down the group, the mass of the atom increases. That means that a particular number of sodium atoms will weigh more as compared to the same number of lithium atoms. That's all for today. Thank you. Stay home, stay safe.